All right, welcome back. I'm not sure what happened on the last video. It just hung up on me. So just want to stress again on this slide that this is a difficult, I think where students have the most difficulty with entropy is this: for two substances in the same phase with similar molar masses, the substance with the more complex molecular structure has the greatest standard entropy. So let's look at that. Let's look at an example of that. And you have to think about maybe Lewis structures and things like that, but here they are. So the first one up here at the top is just fluorine, diatomic fluorine. It's very simple, and so look at what can happen. There's not a lot that can happen there, and so we have stretching, which can occur. All right, and that's pretty much it. So it's just translational. But then we get ozone. You can have stretching, all right, and that's what you're seeing here. You can see that's called symmetrical stretching. This is asymmetrical stretching, where one goes in, one's out. And then you have this bending back and forth, this up and down bending. So this one has a lot more entropy than this. This has more positions in space, more distribution of energy than this one does. And then to highlight that even more, like you look at rotational energy, and you have, this is all that the fluorine can do, is it can rotate around this axis or this axis, and that's pretty much it. This one has more positions as it rotates either around this axis or this one or this one. So again, you can see that ozone's going to have, it's got a larger molar mass, it's more complex, it's going to have a greater entropy. All right, so it says in cases where an element exists in two or more allotropic, remember what allotropic means? Allotropic is like carbon diamond, and so let's write some examples here. Carbon in the diamond form and carbon in the graphite form. That's allotropes. It's the elements that have different arrangement of the atoms. We just saw ozone, so ozone is one form and oxygen is another form. It's still oxygen, but they're different forms. And it says the form in which the atoms are more mobile has the greatest entropy. So diamond's a lot more fixed. It's a more, you know what a diamond looks like versus the graphite in your pencil with those basal planes of graphite. This is more fixed. Because this only has two atoms, less rotations than this. We just saw that on the previous slide. Ozone's going to have more entropy there, greater entropy. All right, so this equation is really important, and it looks exactly pretty much like the equation we saw in chapter 5 with enthalpy. So if I were to measure the standard change in entropy of the reaction for this general equation up here, it's always products minus reactants. That's what we have in these brackets, products minus reactants. You multiply the coefficient in front of the substance, and then you find its entropy, the entropy of C here. You multiply the coefficient in front of D, multiply that by its entropy you find in a table, and then you subtract the coefficient times the entropy of reactant A and the coefficient and the entropy of reactant B. The most common mistake here is make sure you get the sum of what is in this bracket and this bracket first, and then subtract one from the other. I see students just like try to go this plus this minus this plus this. You made a mistake there, because when you said minus this plus this, you're not subtracting everything in the bracket. So make sure that you add up everything in the brackets first before you subtract them. And then this is just a more compact way to write this. Remember, summation, sigma means summation, so that's what we're doing here. We're adding the products minus the products in brackets minus the reactants in brackets, and so this is just a more compact way to write the same equation. So you need to know that equation, memorize it. You're going to use that equation in your assignment and your quiz and so forth. All right, so it says from the standard entropy values in Appendix 2. So when you're doing these problems in your homework, you may have to look at Appendix 2 in your book. And you can search for that, look at that hamburger thing, and when you get into the book, click on the appendix and it'll have enthalpy and entropies. So all you're going to do here is you're going to look up the entropies of your reactants and your products. And so here is the entropy of the calcium carbonate, here's the entropy of the carbon dioxide, and here's the entropy of the calcium oxide. And then you're going to add up the entropies of the products and subtract that from the reactants. Very easy problems. These are easier than what we've been doing, right? So here it is. If you look at A there, I'm not going to do all of these. You can follow the rest of these by looking at the slide. But here's my products here. So there's my entropy of the products, and these are all 1 to 1 to 1, so the coefficients are all 1. This is about as easy as it gets. And so you have the products, get the summation of that, minus, there's only one reactant, so there's its entropy. And so we would sum up this, subtract from that, and we get an entropy change of 160.5 joules per Kelvin mole. So that's the units for entropy. Either joules per Kelvin or joules per Kelvin mole. Let me just say, what I want you to get out of this, you definitely would expect a fairly large positive value for entropy here, because this is a solid, and all of a sudden you generated a gas. So we're going to see a big positive change in entropy here. Okay. This one, what would you expect? You got 1 mole of gas here and 3 moles of gas here, and it's forming 2 moles of gas there, and it is more complex ammonia, but do you think you would see an increase or decrease in entropy? Now, it's going to be a positive value, but overall, is the change going to be positive or negative? I would say it's negative, because you're going from 4 moles of gas to 2 moles of gas. And the last one, I don't really see much of a change. I mean, you got 2 moles of gas on both sides. This is a little more complex, so it could be that causes a fairly positive entropy change. But here you're just asking to calculate the entropy change. You're not asked to evaluate it. You're just asked to calculate it. So that's pretty much set and done. The only thing I really see students make a mistake on is just not making sure they get the sum in the brackets before they subtract them. All right, so qualitatively, that's what we're getting at. You should be able to look at a reaction and tell me whether it's going to be a positive or negative entropy change. It's important that you can do this. And what you want to think about is the definition of entropy. Does after the change, there's more positions available, there's more gas generated? Those are the kinds of questions you want to think about when you determine qualitatively, is the entropy change going to be positive or negative? So melting, you know that melting, when we go from a solid to a liquid, we are increasing positions that those molecules or atoms can occupy. So this is definitely a positive entropy change. When we go from a solid to a gas, which is actually sublimation, you need to know that. Solid to a gas, you're going solid to a gas, called sublimation. Or when we go from a liquid to a gas, called vaporization, those are going to be positive entropy changes, because we're going from a condensed phase, either liquid or solid, to the gas phase. And the gas phase has a lot more positions available than a liquid or a solid. Temperature increases, that means energy of the molecules or atoms are moving faster. And so if they're moving faster, that's going to be more positions available as well, because they're stretching and bending and more energetic, occupying more spaces in time. Temperature increases are entropy positive entropy changes. And then if we generate more gas, yes, you're going to have more positions available and therefore greater entropy changes. So here's what temperature looks like. So I want you to be able to interpret this graph. So you can see that I think a lot of students make mistakes on this graph when we have it on a national test. They think this is going to have the larger positive entropy because it's a higher peak and we're always looking at peaks. But what you want to look at is like draw a line here. And what you see is very little of what's under the yellow curve at lower temperature has that molecular speed. Whereas this under the red curve has much more, there's many more molecules that have higher molecular speeds. So this red one shows a more positive entropy change than the yellow one. Higher temperature, greater distribution of speeds for molecules, but more molecules are going to have a higher speed at a higher temperature, or greater speed at a higher temperature than lower temperature. Here's some other examples, and I would expect you to be able to look at that first one and go, oh yeah, that's definitely going to be a positive entropy change. And the reason why is because you're going from a solid to aqueous, which means these ions are distributed throughout the water. And so that's going to be a positive entropy change. This one, you would think that that would be a positive entropy change as well. But there's something else going on here. And so I think it's funny those are positive, but I mean, there is something else going on here. Generally, you would expect these to have positive entropy changes. Okay, because you're going from a solid to dispersed. I think those are suspect. We're going to go back and look at that. All right, so let's see if we can answer these. These surely are. I do have a question about that other one. I have to go back and look at it. All right, so let's see if you can answer these. For each process, determine the sign of the entropy change for the system. Decomposition of calcium carbonate solid to give calcium oxide solid and carbon dioxide gas. We just saw that. This is the reactant. These are my products. I generate a gas. That's definitely going to be a positive entropy change. The heating of bromine vapor from 45 to 80 degrees. If you see a temperature increase, that's going to be a positive entropy change. Condensation of water vapor, which is water in the gas phase, on a cold surface, and condensation means we're going to the liquid phase. So we're going from a gas to a liquid. We know that's a negative entropy change. Reaction of ammonia with hydrogen chloride gas. So these are both gases, and we're going to a solid. Gases have greater entropies than solids. So we're going from a gas to a solid. That's going to be a negative entropy change. Dissolution of sugar in water. Yes, just think about it. Here's the water, and initially the sugar's in a pile here. That's less entropy than if you have the sugar molecules distributed throughout the water like so. So this is going to be a positive entropy change. So those are not hard. Just think about, is there more positions to occupy? If there is more positions to occupy, then we're going to have a positive entropy change. All right, let's talk about the second law of thermodynamics and the third law of thermodynamics. So the second law of thermodynamics, we're looking at the relationship between entropy and heat. And here's the relationship. The entropy of the surroundings. Now notice this is not the system. This is the surroundings. And you go, what's the surroundings? Well, okay. The thing you're interested in is called the system. I'll call it SY here. Everything surrounding the system is your surroundings. We'll call it SU. And together these make up the universe. So SY here, SU outside. So the entropy of the surroundings is proportional to negative the delta H of the system. So what does that mean? That means if you have an exothermic reaction, which means it releases heat to the surroundings, so heat's coming out of the system to the surroundings, that negative times this negative here will give us a positive entropy change. That makes sense because we're increasing the temperature of the surroundings. The molecules or atoms surrounding the system are moving faster, and there's more positions to occupy, and therefore more entropy. So what we see here is that the change in entropy of the surroundings is proportional to 1 over the temperature. All right? 1 over the temperature. If we combine these two equations together, we get this equation. And you need to know that equation. I think you're going to have some homework problems associated with that. So the change in entropy of the surroundings is equal to negative the delta change of the system divided by the temperature. Let's go back up this temperature. This is the temperature inside the system. So if the system's temperature is higher than the surroundings, then that's going to, if the temperature is going into the system to heat it up, the surroundings is going to decrease. All right, so the next slide, we know that the overall change in entropy of the universe. Now, again, what are we saying here? We're talking about the system, the surroundings, and all that together is called the universe. Okay? So the change in the entropy of the universe is equal to the change in the entropy of the system and the change in entropy of the surroundings. So let's make sure we memorize the second law of thermodynamics, especially those of you thinking you're going into physics. Says that for a process to be spontaneous as written in the forward direction, the entropy change of the universe must be positive. All right? All right, so the entropy change of the universe must be positive for this to go forward. So you go, why do I need to know this? This is when you get into the Big Bang Theory, and maybe this isn't the best theory, but that's what we're going by. So if everything started from a point, and then it exploded, and it sprayed out all the energy and mass that we have in the universe, the entropy of the universe is increasing. And that's what this is saying. The entropy of the universe must be positive. So most scientists believe that the universe will keep expanding. And eventually it'll slow down, it gets slower and slower, and then it kind of comes to a resting point. But there is also some people who think this happens. An equilibrium process is one that does not occur spontaneously in either the net forward or net reverse reaction, but can be made to occur by the additional removal of energy to this system at equilibrium. So what they're saying here is, like, if we're looking at H2O liquid going to H2O solid, we're making ice here. This is a reversible process. We've talked about reversible process in equilibrium in the previous chapters. And depending on whether we remove or add energy, we can affect which way this reaction is going to go. So there are some scientists who think the universe right now is in the expansion phase, but at some point it'll start contracting. Now, most do not believe that today, And that's called the big crunch, that everything starts kind of going back to where it started. Like we're in the forward phase of the reaction. We haven't reached equilibrium yet. So that's where we are as far as, that's where this law comes from, is thinking about the universe. All right, so here we're going to say, determine if each of the following is a spontaneous process or a non-spontaneous process or an equilibrium process at its given temperature. All right, so what do you guys think? So the first one is you're taking two gases, 2 moles of gas, and you're converting it to 2 moles of hydrogen iodide. What do you think? Equilibrium or not? Or spontaneous or not? Well, how are you going to figure it out? That's the question. So you can make a guess. You could maybe look at it and see. But the way you're going to figure these out is by looking at the entropies, the standard entropies that you're going to look from a table. All right, so here we go. We're going to take our product minus our reactants, product minus the reactants, and then we're going to calculate the entropy change, and that's what we did here. Then you're going to look up the delta H's of formation. This is again from chapter 5. Again, if you don't remember enthalpy changes of formation, you need to go back in chapter 5. But here's our products minus the reactants. Again, those are in a table, and we calculate the standard enthalpy of the reaction. Then we're going to plug it into this equation. The delta S of the surroundings equals negative delta H of the reaction divided by T. Now here's where most students make a mistake. This is in kilojoules per mole. This is in joules per Kelvin mole. These have to be of the same unit before you add them together. All right, so here's what we do. We plug in the negative 10.5 kilojoules per mole, multiply that by this negative here, divide by the temperature, 273 Kelvin, 0 Kelvin, right? And we get this for our answer, and then we're going to convert that into joules per Kelvin mole. Why? Because to find out what the change in entropy of the universe is, we got to add the system to the surroundings. So the reaction is the system, and the delta H of the surroundings we just calculated using the delta H of the delta S of the surroundings is we just calculated by calculating the delta H of the system or the reaction divided by the temperature. And so that's where we get this number. Okay, right there. When we add these two together, we get 59.5 joules per Kelvin mole. The delta S of the universe is positive, therefore this reaction is spontaneous at 0 degrees Celsius. All right. So what are we doing here? We're calculating delta S from the table, which is the system. If you want to think of this as this is the standard, because it's the reaction, that is our system. That's what we're interested in studying. We calculate delta H, the enthalpy, the standard enthalpy of the reaction of the system, and that's what we calculated here. But to find the delta S of the surroundings, we're going to plug it into this equation, which we just talked about. And then that you'll solve for delta S of surroundings, and this is what you get. And then you got to convert this to joules per Kelvin mole, so it's in agreement with this one up here. And the delta S of the universe is the system plus the surroundings. We add that up, we get this number here. Because this number is positive for the universe, we know the reaction is spontaneous. All right, let's look at another one. I think you need to see this again. All right, so let's go back and look at the next one there. And I think this is worth looking at again just because you should be able to qualitatively say I know this is going to be positive because I started off with the solid and I end up with a gas. So more than likely, this is going to be positive. If I had to guess, I'm going to say this is going to come out to be a positive change in the delta S of the universe. But let's prove it. Let's prove it. And the thing that's going to come into play is enthalpy. And so this is at 200 degrees. This is at 1,000 degrees. All right. So my guess was that it was positive. And let's look and see. So the entropy change, because there's only one thing, it's products minus reactants. I don't know why they didn't show that, but that's what the entropy change for this reaction is. This is calcium carbonate solid going to calcium oxide, oxide solid, plus carbon dioxide gas. All right, so it's definitely a positive entropy change here for the system. This is, if you don't like reaction, you can write system here. And then the delta H of reaction, which is the system, is products minus reactants, and it comes out to be this. All right, and then here's where we plug in the temperature. So it's 473 Kelvin, and this is a endothermic reaction. That's the problem right there. This requires heat for this to happen. And so it's a negative 177.8 because there's a negative here. Divided by that, we get a negative value here. Negative 376 joules per Kelvin mole. When we plug that in for the delta H of the surroundings, and then this is our system, this negative dominates and this reaction is non-spontaneous. So my guess was incorrect that at 200 degrees Celsius, this reaction is not spontaneous because we don't have enough system increase in entropy to overcome the surrounding entropy. Or the surrounding entropy. And the reason why we do that, is this is an endothermic process, and we're going to have a larger amount of heat to make this number get smaller so that this term dominates and it becomes spontaneous. So that's what they're showing. Let's just go on and look at the next one. So the next one's at 1,000 degrees Celsius. So this is I like this one because it's going to show you what happens. So delta S didn't change for the system. They don't even write it again. But watch what happens here. Got the same delta H, but now it's 1273. It's 1,000 degrees plus 273 to make it Kelvin. This number's less than it was. And when we plug it into here, this term dominates. We get a positive value here, and then this reaction becomes spontaneous. So the change in entropy of the universe becomes positive at 1,000 degrees Celsius versus 200 degrees Celsius. That's a good problem because it looks like qualitatively, just looking that it's a gas, gas generated, you would think delta, that it'd be spontaneous, but no, this is temperature dependent because it was an endothermic reaction. All right, the third law of thermodynamics, this is a different way to write it. So this is what we generally say the third law of thermodynamics is. In a perfect crystalline substance at 0 Kelvin, absolute zero, you have an entropy equal to 0. All right? An entropy equal to 0. Because what happens is this term becomes 1. There's only one position. And the ln of 1 is 0. So it doesn't matter what the Boltzmann constant is. Entropy is equal to 0. So I want you to know the third law of thermodynamics. You need to be able to speak it, apply it, and then use it as an equation. Third law of thermodynamics. A perfect crystalline solid at 0 Kelvin, that means it's a theoretical point. 0 Kelvin means no movement whatsoever. Even the electrons have stopped moving in the atom. So it is a theoretical point. For a perfect crystalline solid at 0 Kelvin, you have 0 entropy. So here we have what the third law of thermodynamics looks like. In the solid phase, the entropy is much less than the liquid phase, and here's the liquid phase as we go we are increasing the temperature of the liquid. Then all of a sudden we have to use entropy to increase to change the liquid to a gas. So that's what's happening here, liquid to a gas, and then we're increasing the temperature of the gas here. So in the verticals, that's where we're going from a solid to the next phase, the liquid. And then the horizontals, that's where we're increasing the temperature. And how do you know that? Because look at the axis. This one's Kelvin, this is entropy. So temperature goes up. Then we have these phase changes in the vertical places, and the temperature changes in the different phases in the horizontal spaces. All right, we're going to stop here. I think that finishes up entropy. I want to introduce Gibbs free energy as a clean, as a new part. So we'll stop here, and then I will do one more video on Gibbs free energy, and that'll finish up chapter 18.